Welcome to this third lecture in EE557. In the last lecture, we have seen the concept of conditioning or random variables. So when one random variable is given or some information about some random variable is given, then if the random variables are not independent, then we can gain some information about the other random variable. Well, in this lecture, we are going to solve a long example related to Gaussian distributions. If two random variables are jointly Gaussian distributed, then we can say that the conditional distributions are also Gaussian. So Gaussian distribution is very, very important, and it's going to be very important in this course as well. So we're going to see that when the linear systems are actually derived by Gaussian noises, then all of the posterior distributions of the state would also become Gaussian, so which would be extremely important, and it's going to be the fundamental result that would lead to the Kalman filter. So in this lecture, we're going to consider two scalar random variables, x and y, and then we're going to try to calculate the conditional distribution px given y. Well, let us start. So we are given x and y, random variables in R. Let us say that they are jointly Gaussian. Jointly Gaussian distributed. When two random variables are Gaussian distributed, when both of them are Gaussian distributed, they do not have to be jointly Gaussian distributed. So jointly Gaussian distributed means much more than individually random variables being Gaussian distributed. Okay? So this statement tells us really a lot. It tells us that individually these random variables are Gaussian distributed, and furthermore their joint distribution is also a Gaussian distribution. So the task is simple. Find probability x given y. So we need to find this conditional distribution for these random variables. So what happens when y is given to the density of x? So in order to continue, I will define a vector. This vector is going to be called z, and it's going to be composed of both of the random variables x and y. And then I'm going to denote the expected value of z, just like this, expected value of z, and it's going to be the vector composed of the expected values of x and y. And if I define the covariance of z, so expected value, so let us say that this is sigma z, it is equal to z minus z minus z bar transpose, and this is going to be a 2 by 2 matrix. So on the diagonals, I would have the marginal variances of the random variables x and y, and I would have the cross variance sigma xy in the off-diagonal terms. Okay? The matrix, the covariance matrix, has to be always symmetric, and it has to always be positive semi-definite, as we have shown in the last lectures. So now I can actually write the distribution of z. If x and y are jointly Gaussian distributed, then z is Gaussian distributed. Okay? So I'm going to show pz, and this is going to be at the same time p of x and y, the joint distribution of x and y. Okay? This is going to be, we will show the Gaussian distributions with a calligraphic n, like this, and this is a distribution over the random variable or random vector z. The mean is z bar, and the covariance is sigma z. Okay? If I now write the Gaussian distribution expression here, this is going to be 1 over square root, I would have 2 pi sigma z determinant, and I would have exponential minus 1 over 2, the quadratic form z minus z bar, sigma z inverse times z minus z bar here, and I would have a transpose here. So this is a definition of a multivariate Gaussian distribution. Okay? So now we can also see the individual distributions of x and y here. So if I write px, then this is going to be a normal distribution. In this case, since x is scalar, this is going to be a univariate Gaussian distribution. In that case, this is a distribution over x. The mean is x bar, and the variance is sigma x. And py is this, normal y, y bar, and sigma y. Okay? Now, if I write the univariate Gaussian distribution, it's going to be the scalar version of this one. So it's going to be 1 over square root determinant. In this case, I don't need determinant because the variance is just a scalar. But let us still remain consistent with the earlier notation here. So I have sigma x. So I can remove the determinant here. It really doesn't matter. So I have exponential minus 1 over 2. And I would have the inverse of the variance. You see that here I have the inverse of the covariance. In the scalar case, I can write the inverse of the variance like this, scalar inverse, and I would have y minus y bar square. Okay? So in order to be brief here, I'm going to define some variables now. So let us define z tilde, which is equal to z minus z bar. Similarly, I will define some tilde variables for x and y. This is x minus x bar, and y tilde is y minus y bar. Okay? Using this notation, I can actually show the distributions in a summarized way. So I would have P of xy, the joint distribution of x and y. Here, I will write this distribution in terms of tilde variables. Okay? So I would have 1 over determinant 2 pi sigma z, and I would have exponential minus 1 over 2, I would have z tilde transpose sigma z inverse and z tilde here. Okay? And I'm going to need here py as well. So I would write py is equal to 1 over, I'm removing the determinant here because this is just a scalar inside, 2 pi sigma x, and I have exponential minus 1 over 2, 1 over sigma y, and y tilde square. Okay? So now I'm ready to actually calculate the conditional distribution. We know that Px given y is the division of the joint distribution to the marginal distribution in the conditioning. Okay? So I need to calculate this ratio here. And this is going to be, I will take this here, 1 over square root 2 pi sigma z, determinant here, and I have exponential minus 1 over 2 z tilde transpose sigma z inverse z tilde. Here really there are lots of variables and I can make a mistake. I hope I can catch it myself here. If I were in a real classroom, it would be really nice for the students to actually correct me. So I would have square root 2 pi sigma y and exponential minus 1 over 2, I would have 1 over sigma y, y tilde square here. Okay? So now the only thing remaining is to carry out this division and see what the resulting distribution would be. So here the first thing that I'm going to do is to calculate these coefficients here. So I need to calculate this ratio. 1 over square root determinant of 2 pi sigma z divided by, I would have 1 over 2 pi sigma y. Okay? Now let us calculate this determinant. Determinant of sigma z is nothing but the determinant of that matrix, sigma x, sigma y, minus sigma xy squared. Okay? But here I need the determinant of 2 pi times sigma z. We know that if I multiply any square matrix with a scalar alpha, determinant is multiplied by alpha to the n. Okay? This is true for all A in Cn by n. Okay? As a result, when I multiply the matrix sigma z with 2 pi, and when I take the determinant, since it's a 2 by 2 matrix here, the determinant of 2 pi sigma z is going to be 2 pi square times sigma x, sigma y, minus sigma xy square. Okay? Now here I will just write the resulting quantities. Square root, I would have 2 pi square, and I would have the determinant here, sigma x, sigma y, minus sigma xy squared, divided by 1 over square root 2 pi sigma y. Okay? Now here, this 2 pi cancels one of the 2 pi's in the numerator, and I need to divide this quantity, this determinant, with sigma y, and that is going to give me 1 over, sorry, the equality signs are really in bad positions now. So I would have 1 over square root 2 pi times this determinant divided by sigma y. It is going to be sigma x minus sigma xy squared divided by sigma y. Okay? So I would have just some term here, sigma x minus sigma xy squared divided sigma y here. Okay? I'm just going to call this quantity as this, 1 over, so I would have 2 pi sigma x given y. Okay? So this ratio is nothing but 1 over square root 2 pi times another variance term, which is given by this. So here my definition for this number is sigma xy is equal to, I would have sigma x minus sigma xy squared divided by sigma y. Okay? So now we have calculated this coefficient here. Now the remaining thing is to calculate these exponentials. I know that I need to calculate this quadratic form minus this scalar here. Okay? So I need to calculate z tilde transpose sigma z inverse times z tilde minus 1 over sigma y tilde square. Okay? So now let me write z tilde transpose. So it is going to be x tilde y tilde transpose times the inverse of that matrix, sigma x, sigma xy, sigma xy, and sigma y inverse times x tilde and y tilde. Okay? This is this quadratic form, and I have the inverse still, minus 1 over sigma y tilde square. Okay? Let us now calculate the inverse of this matrix. So I will first substitute 1 over determinant here. The 1 over determinant is going to be sigma xy, sigma x, sigma y minus sigma xy squared times this vector here, x tilde y tilde transpose, and I would have the adjugate of this matrix here, change the places, change the signs, times again x tilde y tilde minus 1 over sigma y tilde square. Okay? So now let me write this determinant here. This determinant here is nothing but I will write this determinant in terms of sigma x given y. So this determinant is nothing but sigma x given y times sigma y. Okay? So this is equal to 1 over sigma y times sigma x given y. And then I will expand this quadratic form here. It is going to be sigma y times x tilde square minus 2 sigma xy x tilde y tilde, and I would have plus y, so I have sigma x times y tilde squared. Okay? And I would have minus 1 over sigma y tilde squared. Okay? So now let me try to write these terms. So here sigma y expand this multiplication here. Sigma y divided by this is 1 over sigma x given y times x tilde squared minus 2 sigma xy given sigma xy. This is going to be x tilde y tilde plus sigma x given sigma y, divided by sigma y, sigma x given y, minus 1 over sigma y times y tilde, there's a square here. Okay? So now let us calculate this difference here. That is going to be, I will multiply the second quotient here with sigma x given y, both numerator and the denominator. It is going to be sigma x minus sigma x given y divided by sigma y, sigma x given y. So if I subtract sigma x given y from sigma x, you're going to see that we will get sigma xy squared divided by sigma y divided by sigma y, sigma x given y. Okay? Now this surely gives us sigma xy squared, sigma y squared, and sigma x given y. Okay? Now instead of this number, I can use that. And on the way, I'm going to take 1 over sigma x given y parenthesis. It is 1 over sigma x given y. This is going to be x tilde squared minus 2 sigma xy given sigma y x tilde y tilde plus, remember I'm taking 1 over sigma x given y parentheses, so this would be sigma xy squared, sigma y squared, and I would have y tilde squared. Now I want you to concentrate on this parenthesis, the term in this parenthesis. So you see that this is actually a full square, a complete square here. All right, so I really do not have to add anything or subtract anything to complete this into a full square. So this is actually 1 over sigma x given y times x tilde minus sigma x y divided by sigma y times y tilde square. Okay? So this is already a complete square, which is quite fine. It's the magic of Gaussian distributions. So now I'm going to go back to this formula and we'll substitute this ratio here, and then we'll substitute this exponential terms here. So Px given y here is equal to that ratio here. The coefficient ratio is 1 over 2 pi sigma x given y. And I would have here exponential in minus 1 over 2 parentheses. I would have this term 1 over sigma x given y times, instead of x tilde, I will write x minus x bar minus sigma xy given sigma y, divided by sigma y minus y bar. Okay? And I would have the square of this thing. Now I want you to think about this term here. I have like a univariate Gaussian coefficient here, and I have some terms resembling again univariate Gaussian terms in the exponential. So I would like to write this thing as a normal distribution. Px given y is equal to normal distribution. So it is going to be a normal distribution over the random variable x, and instead of mean, what do I have? This thing that I subtract from x is going to be my new mean, x bar plus sigma xy divided by sigma y, and I have y minus y bar here. And what is the variance of this univariate Gaussian distribution? We see that it's going to be this sigma x given y, which is that term. So I have sigma x minus sigma xy squared divided by sigma y. Okay? So this is our final result. This is the conditional distribution of two jointly Gaussian distributions when two jointly Gaussian random variables when one of the random variables is given to us. Okay, y is given to us, and we are looking at the conditional distribution of x given y. Okay, it is again a normal distribution, and you see that the mean is modified from the actual mean or marginal mean of the axis distribution, and the variance is also modified here, as you see. So from this result, actually, I can derive the conditional mean and conditional variance of the random variable x given y. Okay? So here the first thing that I'm going to write is this, px. It is the marginal distribution of x, and it was given like this, x, x bar, and sigma x. Okay? Now you see here that this distribution, it can be called a prior distribution for x, and I have px given y. Now this can be called as the posterior distribution of x given y. Okay, I can write this once more. And okay. So now what are the changes here in this distribution? The mean is modified from where to where? The mean, if y is given to us, the mean of x is modified from x bar to x bar plus sigma xy, sigma y, y minus y bar. Depending on the value of y, the posterior mean of x changes. If y is exactly at its mean, if the measured y is exactly at its mean, the mean of x does not change from the posterior to the prior, from the prior to the posterior distribution. But if y is larger than the mean, then I make a correction on the prior mean of x. Okay, and on the other hand, depending on the sign of the cross variance here, depending on the sign of sigma xy, I can either increase or decrease the prior mean x bar here. So when I look at this formula, this term acts as a gain in this correction. Okay? When we see the value of y, we make a correction on the mean of x, expected value of x, and my correction size depends on this gain. In the literature, this type of gain is actually called a Kalman gain. Okay? And actually these formulas are somehow the basis for a Kalman filter. And I see that the variance is modified with the measurement y into this, sigma x minus sigma xy squared divided by sigma y. So we see here that the variance of x, the prior variance of x, when we measure y, changes from this one into this one. Okay? So I see that the term that I subtract here, sigma xy, can be positive or negative, but we see here that sigma xy squared is always positive or 0. Okay? So therefore I am always subtracting here some positive number or 0 number from the prior variance. So I see that this number is actually always smaller than or equal to the prior variance. So when we measure y, the variance of x gets smaller, which means that its uncertainty is actually decreased. Okay? So the measurement of y brings us some information so that the variance actually gets smaller when we measure y. An interesting thing here that we see is that this decrease in the variance is not dependent on the actual value of y. This is the magic of Gaussian random variables. In general, in a conditional density, in the decrease in the variance might depend on the actual value of the measurement y here. But here we see that in the Gaussian case, the actual value of y does not matter. The variance decrease in x is always fixed and independent of the value of y here. Okay? So I can write here the expected value. So I can actually write expected value x given y. This is going to be equal to this formula here, x bar plus sigma xy given sigma y minus y bar. Okay? And the covariance of x minus expected value x given y, x minus expected value x given y, transpose, I should not write here transpose, because this is already a scalar, it's correct, but still, it's loss of characters. So I would have here this expected value given y is equal to this variance, x minus xy squared sigma y. Okay? So these are called posterior mean. Posterior because it is obtained after we measure y, and this is called the posterior variance. So now I want you to take the expected value of this posterior mean with respect to y. You see that this expected value is still dependent on y. Therefore, this expected value is still a random variable because it's dependent on the random value of y. Now, take the expected value of this posterior mean with respect to y. So this expected value is with respect to y. What do you get? So this is a linear function of y. So all I'm going to do is to substitute the expected value of y here. So this is going to be x bar plus sigma xy, sigma y, y bar minus y bar. So this y changes into its expected value. So this is 0. So it's just going to be x bar. So this is going to be expected value of x. So you see here the actually confirmation of the iterated expectation law, or law of total expectation. Okay? Try to do it on the covariance. Take the expected value of the covariance with respect to y. But I see that the covariance is not actually dependent on y. It's a deterministic quantity here. So this thing gets out of the expectation directly. So expected value of this conditional covariance would be itself. Okay, this is deterministic. It doesn't depend on neither x nor y. Okay, so if I take expected value of, with respect to y, of course, expected value of x minus ex given y squared given y. So this expectation is with respect to y. It's going to be the same. So why is this not equal to sigma x? Isn't that the law of total expectation? So this is definitely, in general, this is not equal to sigma x, which is the expected value of x minus x bar square. Okay? Why is that? So here I can actually give the same result for the random vector cases. So if x and y are not scalars, but they are actually vectors, a very similar result would also hold. Okay? So suppose that x is in Rn and y is in Rn. Okay? So this is the, let me write here first, generalization to the vector case. So in this case, my x is a vector. X is in Rn and y is in Rm. Okay? And in this case, my z is distributed like this. P of z is again distributed like this. Z bar, and sigma z. But this sigma z would be given like this. There would be matrices here, sigma x, sigma y, sigma xy, and sigma yx. Okay? So in this case, this is a partitioned matrix. Sigma x is an n by n matrix. This is in total n plus m times n plus m matrix. And here, these two terms in the off diagonal might not be equal. Why is that? Actually, they are almost equal, but they are equal up to a transpose. Okay, sigma xy is equal to, sorry, here sigma yx is actually equal to sigma xy transpose. Okay, so definitely even the sizes of these matrices really do not have to be equal. Therefore, these two matrices cannot be equal in general, but they are transposes. All right? So in that case, the marginal distribution of x is, so this is pxy, and this is normal x bar sigma x, and py is equal to normal y, y bar, and sigma y here. Okay? Now let us try to generalize this formula here. So the generalization, it is actually, if you want to do the same operations on this partition matrix, then you have to use some rules for taking the inverse of partition matrices. Okay? If you use those rules, then you can invert such a partition matrix in terms of its partitions. Okay? And then you can try to derive the same expression. So here I will not do this calculation in the class, but I will leave it to you as an exercise. So invert this matrix using the matrix inverses for the partition matrices, and then try to calculate the px given y here. Px given y, it is going to be again a normal distribution over the random vector x. And what can we say about the mean? The mean in the scalar case was like this. So it is going to be really similar. X bar is going to be here, plus I would have a gain here, times y minus y bar here. Okay? So here the gain is obtained as follows. There is a sigma y inverse here. All right? So the gain is going to be sigma y inverse times sigma xy. Okay? So in general, then this gain is an n by m gain matrix, and this is actually called the Kalman gain in the literature. And what about the covariance? The posterior covariance would be given by the similar formula. There is again sigma y inverse somewhere, but what about sigma xy square? In general, this is going to turn into the following. Sigma x minus, I would have sigma xy and sigma y inverse times sigma yx here. In the scalar case, sigma xy and sigma yx were equal, so we had just the square of that scalar. And this was a scalar, so we had the inverse of 1 over that scalar here. But here I have this formula. Okay? So this is the generalization of this scalar result to the vector case. So now I can actually write this as sigma x minus sigma xy, sigma y inverse, and sigma yx is nothing but sigma xy transpose, so I can write sigma xy transpose here. Okay? So that would give me a more similar formula to the scalar case. Now the last thing that I'm going to do here is to show you what is going to happen when I have sigma xy equals to 0. If sigma xy is equal to 0, then what does this mean? This means that the x and y are uncorrelated. Remember, this is the cross covariance matrix here. This is the marginal covariance, cross covariance. Okay? So if sigma xy is equal to 0, so this would mean that x and y are uncorrelated. Okay? If this matrix is equal to 0, what is going to happen to this distribution? In that case, px given y is going to be normal distribution x And I would have this, since this sigma xy is equal to 0, this gain is equal to 0. So whatever y is, this is going to be x bar. And I would have, this thing is going to be equal to 0. This subtraction would still be equal to 0. And I would have just sigma x here. So you see that if the cross-covariance matrix is exactly equal to 0, then Px given y turns into the prior distribution of x. Okay? I have just this one. What does this mean? When x and y are uncorrelated, the conditional distribution of x given y happens to be the marginal distribution of x. It doesn't depend on y anymore. But this is we have seen in one of the last lectures that this condition means the independence of x and y. Okay? So here x and y are independent. Okay? So we see here something very, very important. So in general, uncorrelatedness does not imply independence. In general. Okay? Remember, independence implies uncorrelatedness, but uncorrelatedness does not really imply independence in general. But in the Gaussian case, this implication would be correct. Okay? In the Gaussian case, uncorrelatedness implies independence. So a weak dependence form would imply total independence. Okay? So this was the case of Gaussians, and here the final formulas that I can write maybe is the Ex given y. This is this formula. In the later parts of this course, we are actually going to use these formulas, and I have covariance x given y. I can define this as sigma x given y here. And that is equal to this formula. And you see that in the vector case, the covariance, the posterior covariance, does not depend on the actual value of y either. All right? So properties are generalizable to the vector case. Scalar properties can be generalized to the vector case. Okay? So this was just an example and the Gaussian case of conditional random variables. So this is going to be the end of this lecture. In the next lecture, we are going to see last important tools in probability theory that we would be using quite often in this course, and they are going to be the total probability theorem and the Bayes rule. And the final thing that we will see about random variables would be the functions of random variables. And there we are going to see that linear transformations of Gaussian random variables would lead to Gaussian random variables again. So which is an extremely important property of Gaussian distributions. They are independent under linear transformations. But that's going to be all for this lecture. Thank you very much for watching. Bye-bye.